In this video, we'll talk about calculating the pH at several points in a titration and explaining what we mean by a titration. So here's our setup. We're going to titrate 50 milliliters of acetic acid with 1.0 molar NaOH solution. What this means is that we have 50 milliliters of the solution. So in practice, maybe we would have it in a flask, 50 mLs, and this is 1.0 molar CH3COOH. By titrating in, we're not starting with a specific volume. What it means is we're going to take some NaOH and put it in a delivery system like a burette, where we can slowly drip it into the solution. So titration is just another way to say that we are going to add one solution to another, where we can very carefully control the volume add. So what we're going to do is look at what happens as we do this titration. So for adding NaOH to CH3COOH, the first question is, what is the net ionic equation for the reaction that is going to occur as we're titrating? Alright, and the answer there will be B. As we add the NaOH to the solution, we end up with OH minus as a major species, plus the weak acid. So the strong base will react with the weak acid, and this is going to make its conjugate base plus water. The sodium from the NaOH is going to be a spectator on both sides of this reaction. And this right here, remember, this is the net ionic equation for a strong acid plus a strong base. But when we have a weak acid, it's going to react to make its conjugate plus water. Okay, so we're going to look at a few points in this titration to see what kinds of equations that we use as we go through this process. So we're going to look at several different points. We'll look at the very beginning before we add any of the strong base. We'll look at what happens after we've added 10 milliliters, after we've added 25, and after we've added 50 milliliters to this original solution. Okay, so let's look at the first point. At the very beginning, we have 50 milliliters of a 1.0 molar acetic acid solution. Haven't added any base. The first thing we'll do is identify the major species. So in this case, we have the acid. It hasn't dissociated yet, so that's all we're going to write. And we have the water. So we have a weak acid and the water, which can be both. So can we use the Henderson-Hasselbalch to calculate the pH of this solution? Right, the answer is no. We only have a weak acid, there's no conjugate, so we don't have a buffer, we can't use the Henderson-Hasselbalch equation. So how would we calculate the pH? Well, let's write the reaction that's going to happen. So we have our major species, and we know that it's in equilibrium, so we will get this reaction. This is the equilibrium reaction that we saw just for regular weak acids. We'll have to find the K for this. If you look it up for acetic acid, this is 1.8 times 10 to the negative fifth. And so now we can just make an ice table to calculate the pH. So if we have our reaction, we set up our ice table. So we are starting with a 1 molar solution. And we don't have any of the conjugate base and no noticeable amount of H plus yet. So that means we're going to lose the weak acid and make its conjugate plus the H plus. And so at equilibrium, using the small x approximation, would still be about 1 molar of the acid and would have x of each of them. So we get our Ka is equal to x squared over 1. And so to solve for x, this would be the square root of 1.8 times 10 to the negative fifth is equal to x. So x is equal to 4.24 times 10 to the negative third. This is also equal to the concentration of H+. So the pH is equal to the negative log, the concentration of H, and this is going to be equal to 2.37. So what happens at the second point of this titration? So here, we're going to add 10 milliliters of the NaOH to the solution. The major species then, before this happens, are our weak acid, and we've added the strong base, so it's going to split up into the sodium and the strong base and water. So the OH minus is going to react with the CH3COOH to completion. This means we're going to have to do a stoichiometry reaction and make a before and after. So here we have our acid reacting with the base to give us the conjugate plus water. Remember, we have to convert these to concentrations, so 50 milliliters times 1 molar is going to give us 0.050 moles to start with, and for the base, 0.010 moles. And we don't have any of the conjugate weak base to begin with. OH minus is going to be the limiting reagent in this case, so we'll minus 0.010 moles from each, and add that to the products. And so after this reaction, we have 0.040 moles of the acetic acid left. We've used up all the OH minus, and we end up with 0.010 moles of the acetate. After we've done this reaction, our major species are now the weak acid, its conjugate base, water, and sodium. So do we have a buffer solution? Yes, since we have the weak acid and its conjugate base as major species, we have a buffer. So we can use the Henderson-Hasselbalch equation to calculate the pH. So the pH is going to be the pKa plus the log of the base divided by the acid, and this is going to give us 4.74 minus 0.60, and that's equal to a pH of 4.14. So after adding the first 10 milliliters of base to the solution, you can see we've changed the pH by a decent amount, by about 2 units. And this actually makes sense because remember, we started with a solution that was not a buffer solution, it was just weak acid, and so when we add some base, we get a change. So now the solution at the end is a buffered solution with a pH of about 4.1. So let's look at the next step in this. So we're now going to take the solution and make it so that we've added a total of 25 milliliters. So this means that we've added 15 more milliliters from our buffered solution. Okay, so let's look at how we would set this one up. First, we write the major species before the reaction happens. And we see that the strong base will react with the weak acid to go to completion. We'll do the stoichiometry reaction, and we'll do this using a before and after table. And here again, we're still starting with 0.050 moles of the acid. We've added a little more base at this point, so that's 0.025 moles. And we don't have any of the base to begin with. This is still the limiting reagent, so we'd still lose 0.025 moles of the base and make that much of the conjugate base. And so after the stoichiometry reaction, we end up with 0.025 moles of the acetic acid. We've used up all the strong base, and we end up with 0.025 moles of acetate. This point has a special name, so when we've used exactly half of the HA up in a titration, we call this the half equivalence. So at the half equivalence point, our major species remaining are going to be our weak acid, the conjugate base, water, and any ions used to make the salts. Do we have a buffer solution? Yes, we do. We have the weak acid and its conjugate. And so we can use the Henderson-Hasselbalch equation to calculate the pH. So plus the log of our concentration, or moles since it's in the same solution in this case. And you'll notice, actually here at the half equivalence point, that because we've added half as much of the strong base as the original acid, the amount of conjugate base at the end is going to equal the amount of conjugate acid. If these two values are equal, which will always be the case at the half equivalence point, this log value here is going to be the log of 1. And the log of 1 is always equal to 0. So at the half equivalence point, the pH in this case is just going to equal the pKa, which for acetic acid is 4.74. So this is important to note. No matter what the system is, if you have a buffer at the half equivalence point, or the amount of conjugate base is equal to the weak acid, the pH is just going to equal the pKa. Okay, and let's look at the last point on this curve. So if we've had 50 milliliters of the acetic acid, and we've added 50 milliliters of NaOH, our major species, we're going to react to completion. This is going to be as a stoichiometry reaction. So we'll use our before and after table. And you'll notice, since we have as much base as acid, both of them are going to be reacted to completion. So in this case, we end up with none of the weak acid. We've used up all the base, and we have just acetate left over. Again, this will be called the equivalence point, where the moles of the strong base are equal to the moles of the initial weak acid. In this case, all of the weak species is used up. And so what do you think the pH at the equivalence point would be in this case when acetic acid is titrated with NaOH? The pH will be greater than 7. It will be equal to 7 if it's a strong acid plus a strong base. But in this case, because it was a weak acid plus a strong base, what we've done is we've neutralized all of the weak acid. But if we listed the major species after that last reaction, we have now this conjugate base left over in the solution, which will make the solution basic. Okay, so let's calculate the pH for this one. Here's the major species that remain. We do not have a buffer in this case because there is no weak acid remaining. So we can't use the Henderson-Hasselbalch equation. And when we write the reaction that remains, we can see that we end up using an ice table. To get the K for this reaction, so let's go ahead and write it out, we can see that we'll need the KB. So the KB is going to equal our 10 to the minus 14th divided by the Ka, and we can use that for our reaction. So when we're using the ice table, something important to remember is we have to use the concentrations. We can't use moles. And remember, to get this point, we had 50 milliliters, plus we added 50 milliliters of the base. So the concentration at this point is the remaining 0.050 moles divided by the final volume, or 0.5 molar. So that's our initial concentration. Don't worry about water since it doesn't show up in the equilibrium expression. We essentially don't have any of the conjugate acid at this point. We've also used up all the base. So in this equilibrium, we have a minus x plus x plus x. And with the small x approximation, we're essentially left with 0.5 molar of the base and x and x. This gives us x squared divided by 0.5 is equal to the Kb. And when we solve for x, we get x is equal to 1.67 times 10 to the negative 5th. This is equal to the concentration of OH minus. If we take the negative log of OH minus, we get the POH is equal to 4.78. And so the pH is going to be 14 minus the POH. And we plug this in and we get 9.22.